Great. Okay, so today's speaker is Charlotte Aten from the University of Rochester, and her talk is on multiplayer rock, paper, scissors.
Hi, everyone. So thank you so much for having me here virtually. And I'm very excited to be able to kick off PALS for the semester. So yeah, I am Charlotte Aten. I'm from the University of Rochester, or I'm a grad student at the University of Rochester. I am also from Rochester. Okay, so, before I do that, okay, so I wanted to say that for those of you who saw me give a talk on multiplayer rock, paper, scissors in Hawaii in 2018, that actually most of the content of this talk consists of things that happened after that conference. And so I will have lots of new things to share with you. I had really just gotten started at that point. And so I have lots of new things to say. Okay, so I always like to start talks on this by saying that in the summer of 2017, I lived in a cave in Yosemite National Park for about a month. And while I was there, I wanted to explain to my friends that I study universal algebra, which can be kind of challenging when your friends aren't necessarily math people. And so I realized that rock, paper, scissors was a particularly simple way to do that. Okay, so how am I using rock, paper, scissors in an algebra context? We can think of rock, paper, scissors as being a magma or an algebra with a single binary operation, where we take as our underlying set the set consisting of rock, paper, and scissors, represented by R, P, and S naturally. And we define a binary operation, F, on the set A, where F of XY is the winning item from among the set XY. And so, for example, paper beats rock in the game of rock, paper, scissors. And so rock times paper is paper. And similarly, since rock ties with rock, or in other words, if both players choose to throw rock, then the people who chose rock win or tie. And so rock times rock is rock. Oh, and I apologize. I am assuming that everyone here is from a culture where there is a game like this. So I didn't give a description of what this game is, but I think most civilizations in the world have had this game. And so two people simultaneously choose an item. In the Western version of it, those items are rock, paper, and scissors, and they have associated hand signs. Okay, and then the rules are that paper beats rock, rock beats scissors, and scissors beats paper. Okay. All right, so I realized that, as interesting as that is, perhaps, I wanted to be able to play a game like rock, paper, scissors with many of my friends at the same time. And naturally, of course, this led me to study the varieties generated by hypertournament algebras. Okay, maybe that's not so obvious, but I'm going to explain how that occurred. All right, so that's sort of my cutesy introduction, and now I'll give an outline of the talk. I'm first going to define rock, paper, scissors and pseudo rock, paper, scissors magmas. Then I'll discuss a numerical constraint on the existence of these algebras relating the arity of the algebra in question and its order. Then I'll talk about regular rock, paper, scissors magmas, which are constructed using a regular group action. Then I'll move on to discussing hypertournaments. And after that, I will have a generation result. I'll give some nice set of algebras which generate the varieties generated by hypertournament algebras, all of which I'll define later. Then I'll move on to talking about automorphisms and congruences of regular rock, paper, scissors magmas. And finally, I'll give some comments on the search for a basis of the variety generated by tournament algebras. Okay. So first of all, I need to describe what I mean by a multiplayer version of rock, paper, scissors. And so in terms that I will define subsequently, the game of rock, paper, scissors is conservative, essentially polyadic, strongly fair, and non-degenerate. These are the properties I want for a multiplayer game. Okay, so I guess before I define those, what do I mean by a multiplayer game? First of all, I'm going to break with convention and refer to a magma or an n-ary magma when I mean an algebra with a single n-ary operation. So magma traditionally referred to what are otherwise known as groupoids or binars. I'm going to just say n-magma or magma when I mean an algebra with a single n-ary operation, which are the only sorts of algebras I'm going to be considering in this talk. Well, okay, unless you count groups, I suppose. All right, so in any case, any n-ary magma has a selection game associated to it. This game has n players, say P1 through Pn, and it's important that each player's seat at the table, so to speak, is labeled either 1, 2, 3, up through n. Each player Pi simultaneously chooses an item, Ai, from our underlying set A, from our universe A. And the winners of a round of this game are all the players who chose F of A1 through AN. So it's possible that no players at all win, or that there's a three-way tie out of 17 players, or any other such thing. Okay. So that's a pretty general concept, but I want to keep it in mind as I talk about magmas interchangeably with games. Okay. So the first property that's nice that rock, paper, scissors has is that the basic operation of the rock, paper, scissors magma is conservative, which means that if I take any n tuple of things from my universe A, then f of A1 through AN is actually one of those A1 through AN. And so thinking of this in terms of the associated selection game, we say that A is conservative when each round has at least one winning player, which is what we would like in a game. I mean, tying is one thing, but we don't want to have a game where everyone loses. That's not what I wanted in any case. All right, so the second property is essential polyadicity. We say that an operation F is essentially polyadic when there is a function G mapping subsets of our universe A to A, so that given any n tuple of things in A, the image of that tuple under F is actually just what we would get by applying G to the set A1 through AN. So this is analogous to being essentially unary or essentially binary, I suppose. This is sort of the variadic analog of that, where the value of this operation really only depends on the underlying set of arguments to which it's applied, and not the order or the multiplicity, as long as it's at least one. And so in terms of the selection game associated to magma A with this an essentially polyadic basic operation F, we think of that game as having the winner only determined by which items are played, and not how many of each item is played. And so I basically took this as an axiom because I would find it somewhat exhausting to play a game with 147 people and have to keep track of, that there were 53 people who chose rock and 27 people who chose scissors and so forth. As long as there's at least one of each item, that's all that we care about. Okay, so the third property that I would like is strong fairness. And so for this, I'm going to write A sub k to denote all of the members of A to the n, or in other words, all of the n tuples of elements of A, which have exactly k distinct entries for some k. So for example, A1, and this is kind of silly, would just consist of all of the n tuples which had all the same entry. or in other words, A1 is the diagonal, and then starting with A2, we have more interesting things. Okay, so we say that an operation F is strongly fair when the preimage of any two elements of our universe under this operation F intersected with these AK, that these have the same size. I always find this condition the hardest to explain, even though what I've written here is, of course, exactly what I mean. So the idea is that the selection game for A is strongly fair when each item has the same chance of being the winning item when exactly K distinct items are chosen by the players for any possible K. And so this turns out to be exactly what you want for reasons that we'll see subsequently. But after I first defined this and started using it, I still look back and find this to be the strangest of the conditions that I chose to study. But it works, even if it's a little odd. Okay, so the final condition that I want is non-degeneracy. I'm going to say that an operation F is non-degenerate, or, well, this doesn't really depend on the operation, I suppose, but I'm going to say that a magma is non-degenerate when it's it does depend on the operation. So an n-ary operation F is non-degenerate when the underlying set A, to which on which F is an operation, is strictly larger than the arity of the operation. And so the reason I want this is basically that if I have an essentially polyadic magma or selection game, and the number of items in my universe is at most the arity of my operation, then I can't have a strongly fair game unless that universe has only one element, or unless the game is actually trivial, or the magma is trivial. Okay, so that's just to keep me from having to continually say not the degenerate case where A is less, size of A is less than or equal to n. All right, so there are other variants of rock, paper, scissors, some of which have all of those conditions that I just listed, and some of which do not. The French version of rock, paper, scissors adds one more item, which is the well. The corresponding game is not strongly fair, but it is conservative and essentially polyadic. So this doesn't have all of the properties I'd like, but it has some of them. In the French version, the rock and the scissors lose to the well, I guess because they fall into it, but the paper covers the well, and that defeats it somehow. Okay. There's a more recent variant of rock, paper, scissors, which is rock, paper, scissors, Spock, lizard. And I can't remember the rules for this one off the top of my head, but the corresponding magma is depicted here with V for Spock, for Vulcan, and L for lizard. This game is actually like rock, paper, scissors in the sense that I've defined previously, in that it's conservative, essentially polyadic, strongly fair, and non-degenerate. Okay, so one can verify that this magma has all of those properties. All right, so I have a version of a known result for two-player games, which is that the only valid rock, paper, scissors variants for two players have an odd number of items. And this is basically analogous to the known thing that there can only exist a regular or balanced tournament in the sense of graph theory when the underlying set has an odd number of elements, or there are an odd number of vertices, in other words. Okay, so in our situation, if we have a selection game with a basic operation which is binary, or in other words, a selection game for two players, which is essentially polyadic, strongly fair, and non-degenerate, and we take M to be the order of this selection game, or the order of this magma, then we have that order must be odd. Conversely, actually, for each odd order, there is such a game. And so I'd like to note that we don't need the assumption of conservativity here. We just need these other three conditions. And the proof, which I won't go into, is essentially that we need M to divide M choose 2. And if this occurs, then going in the other direction, it is possible for us to manufacture such a basic operation, which is essentially polyadic, strongly fair, and not degenerate. Okay. So now I'd like to consider pseudo rock, paper, scissors magmas before moving on to rock, paper, scissors magmas proper. So if I have an n-ary magma, A, which is essentially polyadic, strongly fair, and non-degenerate, then I'm going to say that A is a pseudo rock, paper, scissors magma. When A is an n magma of order M, I'm going to say that A is a pseudo RPS MN magma, and I'm also going to use this notation to refer to the classes of such magmas. Okay, so this is close to what I want for a generalized rock, paper, scissors game. And so there's an analogous result to the one I just described for multiplayer games. And so, and this is the numerical constraint that I had referred to previously in my outline for the talk. If I have a pseudo rock, paper, scissors magma of order M and arity N, or in other words, if I have a pseudo rock, paper, scissors game with M items to choose from, analogous to our 3 items for rock, paper, scissors, and N different players, analogous to the 2 players from the original rock, paper, scissors, then if I take pi of M to denote the least prime dividing the number of items M, or the size of the universe M, then we actually must have that the number of players, or the arity N, is strictly less than the least prime dividing the number of items, or the order of the magma. So conversely, for each such pair, Mn with n strictly less than the least prime dividing M, well, where M is not 1, we have that there exists such a magma. And so the proof is really essentially the same as the binary case. Basically, we just need that M divides the greatest common divisor, or in other words, M divides M choose 2 and M choose 3 up through M choose N. This basically comes from that strong fairness condition and essential polyadicity. And so then if we have that M divides each of those guys, then M must divide their greatest common divisor. And we can go on from there to see that this condition must hold. And if it does, we can again work backwards and show that there always does exist such a magma. Okay. And so this is sharp. This constraint is sharp in that sense. All right. So now I'd like to talk about rock, paper, scissors magmas proper. A rock, paper, scissors magma is an n-ary magma, which is conservative, essentially polyadic, strongly fair, and non-degenerate. So in other words, a rock, paper, scissors magma is a conservative pseudo rock, paper, scissors magma. And again, I'll use notation like RPS MN to denote all such magmas of order M and arity N, or in other words, all such games with M items and N players. And both the original game of rock, paper, scissors and the game rock, paper, scissors, Spock, lizard are RPS magmas. The French variant of rock, paper, scissors is not even a pseudo RPS magma because it's not strongly fair. Some items have a better chance of winning as opposed to other items, even once we restrict to only the situation where a fixed number of items, say 2, are played by the players in question. Okay, so now I do have a general method for producing a game for with M items for N players using regular group actions for all those possible M and N for which that numerical constraint I just referred to holds. But before I actually give the general description of how to do that, I'm going to give an example, which I hope will be much more informative, because the general description of how to manufacture such a thing is a little bit verbose and I think hard to digest in the context of a talk like this. So I'm going to construct a game for 3 players. This is going to be a ternary RPS magma with some universe A and some ternary basic operation F. Since n equals 3, we need that n, or 3, is smaller than the least prime dividing m. And so from that, we must have that our universe contains at least 5 elements, because 5 is the next largest prime. And so our construction is going to use the left addition action of z mod 5 on itself, or in other words, we are taking z mod 5 to be our universe. And so, oh, and of course, this is the cyclic group of order 5, viewed as the integers mod 5 under addition, not the 5-adic integers. Okay, so I'm going to produce an operation which is essentially polyadic and has that the group z mod 5 is acting as an automorphism group of the resulting magma, in the sense that if I take some w in z mod 5 and add it to f of xyz, which is then another member of z mod 5, I actually get that that's the same as f applied to w plus x, w plus y, and w plus z. Okay, so if it were possible to do this, then we would only need to define f on a representative of each orbit of the 1 sets, 2 sets, and 3 sets in the integers mod 5 under this action of left addition by z mod 5. Okay, so I claim it is possible to do this, and I'm going to show you one example of how it can be done. So first we list the orbits of the 1 sets, 2 sets, and 3 sets of z mod 5 under this action. And so in this notation, for example, 1, 2, 4 is actually denoting the unordered set, say 1, 4, 2. And of course, I'm viewing z mod 5 as the set 0, 1, 2, 3, and 4 with the usual addition. Okay, and similarly for these other guys. So 1 is actually representing the 1 set 1. All right, so these are our 5 orbits that we have under this action of z mod 5. Next, we're going to choose a representative for each orbit, say the first one in each row of this table. Oh, yeah. Okay, so these are our orbit representatives. We could have chosen others, but those are just fine. Now, for each orbit representative, we're going to choose a particular element which belongs to that representative. And so our choices are going to be 0 from 0, 1 from the set 0, 1, 0 from the set 0 and 2, 0 from the set 0, 1, and 2, and 0 from the set 0, 1, and 3. We could have made other choices. For example, for 0, 1, 3, we could have chosen 1 or 3, but not 2 or 4, because we want to choose something that's already in our set. So, okay, so now we can use the left addition action of z mod 5 to extend these choices to all members of z mod 5 choose 1, 2, and 3 in the natural way that if, for example, I set 0, 1, 3 to go to 0, then I add 1 to everybody, and I get that 1, 2, 4 should go to 1, and so forth. Okay, so now I can read off from this a definition for a ternary operation by taking that, for example, 2, 4 maps to 2 to indicate that if I apply f to any tuple, or any triple in this case, whose elements or whose components exactly form the set consisting of 2 and 4, so for example, 2, 4, 4, 4, 2, 4, 4, 2, 2, and so forth, the value of f applied to all of these guys should be 2. Okay, so I can in this way, turn this table that I've produced into a ternary operation. The Cayley table for the corresponding 3 magma obtained from this choice of F is given below, where, of course, it's a 5 by 5 by 5 cube, but I can't draw that very well, and so I've split it into 5 separate tables in the natural way. All right, so I claim that this is actually a rock, paper, scissors magma, and that it's conservative, essentially polyadic, strongly fair, and non-degenerate. All right, I'll leave that for you to check. Okay, so the formal definition is basically what I just did. We can take a general group G, some set A, and some arity N, which is strictly smaller than the size of A. And if we have a regular group action alpha of G on the set A, where perm A is denoting the symmetric group or permutation group of A, if we have an action so that each of the extensions of alpha to K sets in A is free for each K between 1 and the arity. Oh, and also the group action is regular. Yeah, so regular group action, each of its K extensions are free. Then we can start making a sequence of choices. If we have such a nice group action on a set, we're going to choose representatives for each of the orbits of K sets under the action of the group. Then we're going to choose representatives for each of those orbits. Then for each of those representatives, we're going to choose an element, and that's what those gamma K of psi are. And then we can, from that, define this map, which takes subsets of at most n things in A to things in A, and use that to produce an n-ary operation in the manner described here. All of this is basically exactly what I just did with the left addition action of Z mod 5 on itself. And so as long as we have so the only real additional constraint that I'm asking for is that we have a regular group action on a set, which is essentially left multiplication or left addition in the case of an additive group, whose extensions have to be free up to whatever n we choose. Okay, so that's the general definition of an alpha action magma, which would be the magma associated to this basic operation.
Sorry, Charlotte, can I ask a question?
Sure.
Yeah, what do you mean by the extensions are free?
So what I mean is that so the extension, so you can extend the action of a group on a set to an action on tuples of that set. So if my K was 3, for example, then I can look at 3 tuples like A1, A2, A3.
Mm-hmm.
And so then, you know, by that action, I can view some element of my group, say sigma, is acting component-wise, and that gives me a group action on the, oh, I guess I want unordered triples, actually. So I shouldn't have written that as a tuple, but that gives me a corresponding action on the triples. Okay, and so in the usual way, and so then saying that this is free means that I want that there should be no group element which fixes everything. So yeah, so in other words, every element, every group element has to take something to something else. There has to be something, yeah. So that's what I mean by a free group action. Does that make sense?
So no group element should stabilize the triple, or should
there should be some triple for each group element. There should be some triple so that sigma applied to that triple is something other than itself. So yeah, so fixed point free group action, in other words.
So every non-identity group element.
Oh yeah, I'm sorry, every non-identity group. Yeah, thank you, non-identity group element, which I think is the standard meaning of a free group action.
Fixed point free group, yes.
Yeah.
Okay.
Yeah. Okay. And regular is free and transitive. Okay.
All right.
All right. So is that okay? Awesome. Yes. So okay. So that's what I need, and it turns out that if you have an alpha action magma induced by some set of choices, these betas are those choices of orbit representatives, and this gamma is the collection of choices of representatives from the individual orbit representatives. Then we have that the resulting magma is a rock, paper, scissors magma. And so the reason that this result holds, although I won't really describe the proof, basically comes down to that this is where I need a regular group action, and I need that these extensions are free in order to get that strong fairness condition. That's essentially why I need those extra constraints. Okay, but basically the thing that I depicted with Z mod 5 before works in general, modulo those constraints being satisfied by the group action. And again, because regular group action is isomorphic in the sense of isomorphic group actions or isomorphic G sets, any regular group action is isomorphic to the left multiplication action of the group on itself. So we can really just always work with that particular action. All right. So in any case, I'm going to define a regular RPS magma as a magma I obtain by using the left multiplication action of a group on itself in order to produce a rock, paper, scissors magma in this way. And so, of course, I need to satisfy this numerical constraint, which is that my arity should be smaller than the least prime dividing the order of my group, which is also then the order of my universe for the magma that I'm constructing. And so, okay, before I go to that, so it turns out that actually this is possible to do in general, and so there are actually regular rock, paper, scissors magmas of any possible arity and order subject to this constraint. Okay, so okay, so now I'd like to switch to talking about hypergraphs, and so basically hypergraphs play the same role in the discussion of N tournament, or in the discussion of N-ary rock, paper, scissors magmas as tournaments play in the discussion of rock, paper, scissors magmas. So for the game rock, paper, scissors, I could actually view it as a tournament, or in other words, a directed graph whose vertices are rock, paper, and scissors, where I draw a directed edge, say from paper to rock, to indicate that rock beats paper, or that paper beats rock in the game, or we might say paper dominates rock. And so similarly, we can view the game of rock, paper, scissors as a directed graph in this way. So the N-ary analog of this is what I call a pointed hypergraph. So a pointed hypergraph consists of a hypergraph, which is a set S and some collection sigma of subsets of S, and also a map, which can be thought of as the pointing of these edges in sigma, which assigns to each edge some element of that edge. So, or in other words, the vertex to which that edge is pointing. So this is not the same as having an oriented hypergraph. It's a bit of a weaker condition, or a bit of a weaker concept. Okay, and so I'll be particularly interested in the N-complete hypergraph as the underlying hypergraph for my pointed hypergraphs. And so this is going to be the hypergraph I'm going to call Sn, whose vertex set is a set S for some, say, finite set, and whose edge set is the union of the sets S choose K for K from 1 through N. And so you can also think of this as the, let's see, K-1 skeleton of the simplex whose vertices are S. Okay. And so a hypertournament then, in analogy with the directed graph definition of a tournament, is that an N hypertournament is a pointed hypergraph. So a hypergraph with this pointing on the edges, where that underlying hypergraph is this N-complete hypergraph for some set S. Okay, and so actually we already have seen one of these, because those choices I made of assigning K sets for K equals 1, 2, and 3 in Z mod 5 to particular elements in order to construct a game for 5 players or for 3 players with 5 items to choose from. This identification is actually the pointing G that we need to produce a pointed hypergraph whose underlying set is the set Z mod 5. Okay, and so this is actually an example we've already seen. And so just like in the binary case, we can think of either an N-ary magma as an RPS magma, or we can think of an N hypertournament as the corresponding object given by this pointing G. Oh, which, by the way, this G is the map that witnesses that the basic operation F of our magma is essentially polyadic. Or it's essentially that map. Okay, so then we can go back and forth between N magmas, or between conservative and essentially polyadic N magmas and hypertournaments in the natural way. Again, that this G is essentially telling us what this basic operation F is, because we're taking F to be essentially polyadic and conservative. And so these are 2 equivalent definitions of hypertournament magma. And this generalizes the correspondence in the binary case. Okay, so so the N equals 2 case of hypertournament is just the classic tournament. These were introduced by Hederlin and Schwadel in 1965. And there's been a lot of work on the varieties generated by tournament magmas. So I actually found the survey by, somebody can please tell me how to pronounce this name at some point, but Venkovich et al. In 1999. I found that survey really helpful. Oh, was somebody going to tell me now, or? Oh, okay, maybe later.
So
I'll have a shot.
okay.
Venkovich. Okay, thank you. All right, so it looks like I'm running a little shorter on time than I had hoped. So, okay, so, okay, so I guess I'm going to write, RPS N to denote the class of all N-ary RPS magmas, regardless of their order. PRPSN to denote the class of all N-ary pseudo RPS magmas, regardless of their order, and TOR-N to denote the class of all N-ary hypertournament magmas. It turns out, just based on just directly from the definitions, that the N-ary rock, paper, scissors magmas are precisely the intersection of these 2 classes, and that the N-ary rock, paper, scissors magmas are properly contained in both. Okay, so so from that, I'm going to denote by Tn the variety of algebras generated by the N hypertournament magmas, which is, as of course I'm sure everyone here knows, equivalent to taking that Tn is all the homomorphic images of subalgebras of arbitrary products of N tournament magmas, or that this is the class of all models of all the identities satisfied by all of the N tournament magmas. Okay, where again, the case N equals 2 is what's been studied for quite some time. Similarly, we're going to define Rn to be the variety of algebras generated by the class of all n-ary rock, paper, scissors magmas, which is much more restricted than a general tournament magma. Okay, so the generation result that I wanted to share with you is that the variety generated by n-ary tournament magmas is actually the same as the variety generated by n-ary rock, paper, scissors magmas. Or in other words, the n-ary rock, paper, scissors magmas generate the variety generated by hypertournament magmas of the corresponding arity. Moreover, this variety, Tn, is generated by the class of finite regular n-ary rock, paper, scissors magmas. And so I wanted to at least go over the proof of this, but I'm not sure how much detail I can go into in the last 5 minutes or so. Okay, so one containment is trivial. All the rock, paper, scissors magmas are tournament magmas. And so since N hypertournament magmas are conservative, any identity holds for the N hypertournaments only when okay, so an identity epsilon in M variables holds for the N hypertournaments if and only if each N hypertournament magma of order M models epsilon. So, so it would be enough to show that each finite N hypertournament magma actually, oh, not belongs to, that was a typo. Is in actually the class of subalgebras of Rn. Oh, well, actually, I took Rn to be the variety, so that's not what I mean either. This is just a silly typo. So, okay, so what it suffices to show is that each N hypertournament embeds into the hypertournament associated to a finite regular rock, paper, scissors magma. Because if my hypertournament or its corresponding magma is T, and I have that T embeds in some magma A, which belongs to the class of all n-ary RPS magmas, and I know that this is a sub-collection of the variety that is generated by all of these guys, then I will know that T actually belongs to this variety as well. Okay, so that's what I mean there. And so it turns out that this is the case. So we get very lucky, and the laziest possible way that we could show that this class generates the variety generated by all hypertournament magmas does indeed that does indeed happen. And so okay, so basically the way that we do this, and I'll be very succinct, although I guess when I post these slides you can look at that, or you can just read the paper. Essentially making all of these choices beta gamma is really painful, and I don't want to have to keep doing that. So the first thing I'm going to do is realize that essentially specifying an RPS magma comes down to choosing, say for each element X of our group, whether X or X inverse is positive or dominates the identity, or is dominated by the identity element. Okay, so I have to actually be able to do that in general somehow. And so the way I do that is by looking at obverse k-sets of a k-set in a group, in a finite group. And so these play the role of inverses. And the important thing is that one can find that actually choosing from among the obverse k-sets for a given k-set, which one is the one which is dominated by the identity element, actually specifies the entire RPS magma that I was calling Gn beta gamma. So there's this one set of choices, which are slightly involved to define, that do the job more succinctly. Okay, and so that set of choices is what I'm calling an n-sign function. It's a choice function on the set of all of these obverse k-sets for any k-set of the appropriate size in my group. Okay, so once we have that concept, which I'm sure people haven't absorbed by this point, but unfortunately I'm kind of out of time, we can actually give the appropriate embedding. We're going to take some finite hypertournament, which is a hypergraph whose edges have been pointed by this function g. And then what we're going to do is take an underlying group, which is a direct sum indexed over the elements of our vertex, of our vertices for our tournament, of cyclic groups of some orders alpha u. And we're going to need that this numerical constraint holds for each of those guys. And we're going to identify the vertex u with the generator of the cyclic group. Then we can define this function, which is what we need to define the appropriate magma, by setting this function lambda of this collection of obverses to be this guy when g of u1 through uk is u1. Any values can be chosen on the other other collections of obverses, and once we do that, it turns out that we actually get a corresponding magma gn lambda, which contains an isomorphic copy of T viewed as a magma. Okay, so so it turns out actually that every finite hypertournament embeds into one of these regular hypertournaments coming from a regular rock paper scissors magma, and so just using those regular rock paper scissors magmas actually is enough to generate the whole variety generated by n-ary tournament algebras or n-ary tournament magmas. Okay, so I am pretty much out of time. I will just quickly say that you can also use that nice group action to get results on automorphisms and congruences of these regular RPS magmas for any arity. And so you can characterize their automorphism groups pretty extensively. It's possible to show when certain exceptional automorphisms exist. Actually, in a particular case of the magmas of the form ZP P-1 lambda, or in other words, the P-1 airy rock, paper, scissors magmas on ZP, you can actually show that there are only so many automorphisms that are the sort of the standard ones. And from this, actually count the number of isomorphism classes of these guys. So in the case of, for example, Z7-6 lambda, there are actually 2,073,600 different choices up to isomorphism. Okay. We can also examine the congruences, and it turns out that, although I won't give the argument, that the congruences are essentially given by partitions of the group into cosets of subgroups. And so that's a bit of an argument as well. And so from this, we can actually completely describe what the lattice of congruences of the regular n-ary rock, paper, scissors magmas look like. Turns out to be the distributive lattice of the maximal anti-chains of this poset that we can construct from our magma. And so, okay, and so then we're able to actually describe those congruence lattices completely. And so I apologize for taking it a little too slow in the beginning and rushing at the end, but the comment I wanted to make about finding a basis for the variety generated by tournament algebras was that, so by the year 2000, this is again just the binary case of what I was just discussing, Jezek, Markovich, Morotti, and Mackenzie had shown that what I was calling T2, the variety generated by tournament algebras in the classic binary sense, was not that this variety is not finitely based. And so to this author's knowledge, that was 20 years ago, but as far as I know, no equational base for T2 has ever been described, aside from saying trivial things like you can take as a base the collection of all the identities that belong to that equational theory, which is not interesting, obviously. And so, okay, so I hope I didn't oversell this, but my thinking is that some of the work that I've done on this project on rock, paper, scissors magmas may be helpful in finding some sort of interesting description of an equational base for this variety, because rather than having to examine all possible tournament magmas of order M to check whether an identity epsilon in M variables holds in this variety, we can look at only the regular rock, paper, scissors magmas of the appropriate arity. So one possible choice is to only look at the identities that hold in those magmas of the form C3M 2 lambda. There are other choices as well, even just in the binary case. And since we have this nice group action that helps us to understand automorphisms and congruences really well, it's my hope that maybe some of that work can be used to actually give a better description of the identities that hold in this variety. But I still haven't actually done that myself. So I thank you guys so much for attending my talk today and for having me here at PALS.
Thank you. Okay, does anybody have any questions or comments that they'd like to ask or say?
Yeah, so I have this is Peter. In your regular rock, paper, scissors algebras, they all the regular was because they were defined from some group action, right?
From a regular group action, yeah.
Yeah. And it looked like in the later proofs, the groups that you used were always abelian groups. Is that in the definition already, or is that just an accident that those are enough to generate?
Yeah, it turns out to be an accident, I suppose, that those are enough. So they're actually. Yeah, so it happens that there are some pretty restricted classes of even abelian groups that suffice to generate the whole variety generated by N hypertournament magmas. And so basically the two types that suffice to use are essentially vector spaces over finite fields and cyclic groups. Either one of those is enough. There are more interesting things that you can say about automorphisms, for example. If you have your underlying group non-abelian. And so in the paper associated to this, I do actually give some examples I give a pretty explicit example using the smallest non-abelian group of odd order. Yeah, it's certainly not necessary to use an abelian group. It just happens that abelian groups are enough.
Mm-hmm. For generating the variety.
Yeah.
So I assume there are also rock, paper, scissors algebras that are not regular, right? That do not come from groups.
Yeah. So I also give an example of that in the paper as well. That's something that in the context of just tournament graphs is something that people had already seen before. All of the regular, okay, so one way of seeing it is that, so rock, paper, scissors magmas are essentially balanced tournament graphs. And so the regular rock, paper, scissors magmas, the binary ones, all have the group that's used to define them acting as automorphisms. And so each one has at least as many automorphisms as the size of its universe or as its order. However, you can construct balanced tournaments with very few automorphisms. And so those cannot possibly be constructed in this manner.
Mhm.
So I give an explicit example of that in the paper as well.
Right, thanks.
Thank you.
So I have a question. Have you looked at the game theory of these rock, paper, scissors games? Are there things happening somehow, interesting things?
So, okay, so I actually didn't, I've never really studied game theory. I'll just say that right away. People do keep asking me though, and so I have at least looked into it enough to see that, you know, that these of course are, you know, games in the game theory sense as well. I know that people have, of course, studied rock, paper, scissors in the sense of game theory. There are various Nash equilibria that you can find for that game, for instance. I haven't even attempted to do anything analogous for these games, although it'd be interesting if someone did. On a related note, I know that there are people who do like rock, paper, scissors game theory in biology with mating strategies. There was a paper in Nature in the 90s about lizards specifically. And I had seen this in doing research on this project a couple of times. And then when I gave a talk at a conference last fall, I was talking to somebody who was like, you know, you should just see if the biologists have done, you know, something that seems like the NRE version of this, because of course, you know, more than 2 types of lizard might be competing, you know, mating at the same time. And I emailed the authors of that paper from the 90s, and like last week I emailed them and I haven't heard back yet. So I still don't know if the biologists have considered the NRE version of rock, paper, scissors. But I do know that there are, there's some possible connection there as well.